Hello, this is section 2.1, vectors in the plane. And it says vectors in the plane, but we're really going to talk a little bit about vectors in space as well. Just because in a lot of situations, it really doesn't make a difference whether it's in the plane or in space. You basically just have an extra number. All right, so before we do that, just in general, a vector is a quantity that has both magnitude and direction. Okay, so when we say magnitude, a lot of times we'll just say length. It means the same thing. It's just basically how long the vector is. And when we say direction, we just mean which way it's pointing. Okay, so like in the plane, it's sort of like, it can point in 360 degrees, whichever way it goes like this. In three space, or in the, just in space in general, it can really just point wherever it wants. All right. So let's look at some vocabulary. And so this is an example of a vector. A lot of times we represent vectors by arrows because the length of the arrow, that's the magnitude, and the direction where the arrow is pointing, then that's of course the direction. All right. So if we have a vector that looks like this, then this point right here is usually called the initial point, and the point that has sort of the arrowhead on it is called the terminal point. Now, if you look over here on the right, all of these vectors are actually considered the same vector. Okay, so when we talk about vectors, really all we care about is their magnitude and direction. We don't care about where they're actually printed in the plane. Okay, so we'll do things with vectors, but we won't really think about where they're positioned. We mostly think about just how it's angled and how long it is. So anyways, these are all what we call equivalent. And what equivalent means is it just means that they have the same magnitude and direction. Okay, so if we look at this example right here, all of these vectors are not going to be equivalent. Some of them are equivalent, some of them are not. Just kind of looking at it, you can probably tell which is which. Because, for example, vector D and vector F, they sort of obviously don't have the same magnitude. Their lengths are different, so those are not equivalent. On the other hand, vectors A, B, and E, even though they are put in different places on the plane, they're actually equivalent vectors. Okay, so in this case, A, B, and E are equivalent, and the other ones are not going to be pairwise equivalent. All right, and so let's keep on going. Okay, so the next, a lot of times we talk about the component form of a vector, and the reason we do that is because really we have two choices. I mean, we can either define a vector as being 2 points, where one's an initial point and one's a terminal point, but that's kind of a waste because usually we don't care about where in the plane or where in space the vector is. We just care about its magnitude and direction. And so if we really only care about the magnitude and direction, then what we can do is we can write it in what's called component form. All right. Sometimes it's called like a representation of a vector. Component form and a representation, those mean the same thing. So if you look at this, it says if you have a vector with initial point xi, yi, and terminal point xt, yt, then the way we can find the component form of the vector is just by doing some subtraction. Okay, and I kind of like the way this one was written a little bit better. And it says given points x1, y1, z1, and x2, y2, z2, then the vector A with representation AB is this. Okay, so we just subtract the x components, the y components, and the z components, and that gives us the component form of the vector. All right, so let's do an example. And this is a situation where it doesn't really matter that it's in 3 space. I mean, we have 3 components here, because we have 3 little components on our points. But if it's in 2 dimensions or 3 dimensions, you do this the same way. You just do subtraction. And what's interesting is like this is a pretty easy concept, but people forget this all the time, and it comes up in this class over and over and over. And so just remember, if you have 2 points, an initial point and a terminal point, and you're trying to figure out the component form of the vector, or a lot of times we'll call it the angle bracket notation. Angle bracket notation is just another way to say component form. The way you do that is you just subtract the x components, the y components, and the z components. All right, so in this case it says find the vector represented by the directed line segment, blah, 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 blah. Okay, so all that's saying is that we have a vector, and its initial point is the point 1, 4, 3, and then its terminal point is the point -2, 1, 1. Okay, and I didn't draw these points correctly. It doesn't really matter how you draw them because we're basically like getting rid of the points. That's sort of the whole idea here. And so what we're going to do is we're just going to subtract the x, the y, and the z. All right, so we're gonna call this vector v. All right, and so I'm going to look at these, and I'm going to notice that the x component on the tip is -2. Sometimes the terminal point is called tip. And then the x component on the tail, which is another name for the initial point, is a 1. All right, so we're going to do -2 minus 1, comma, Okay, and then we just keep doing this. Okay, and so sometimes what people call this is they call it tip minus tail. All right, so that's another way to think about it. All right, so the next component is the y component. So we're going to do 1 minus 4. 1 minus 4. All right, and then the last component is the z component, the one I didn't highlight. So that's 1 minus 3. Okay, and that's really all there is to this. But like I said, this is pretty important. Like we do this all the time as the semester goes on. Okay, and so -2 minus 1, that's -3. 1 minus 4, that's -3. 1 minus 3, that sounds like -2. And then that is our answer. Okay, so in other words, what we did here is we sort of took this vector and we turned it into just the kind of like the generic form of the vector. Like we turned it into having some kind of like position in the plane, or I guess in space in this case, and we turned it into just just having the magnitude and the direction, which is good because the idea of it is a lot of times we want to simplify them. Now, one thing to note is we said these vectors are equivalent. Up here, if I were to do this whole tip minus tail thing for each of these, I would actually end up with the same thing. Okay, so like let's even do this. All right, so this point right here is -2, 4. This point right here is -3, 2. I don't know. Let's do this one down here. All right, so this point, that's going to be 3, -1, and this point right here is 2, -3, like that. All right, and so I'm just going to do tip minus tail. Okay, so for this one right here, that's going to be -2 minus -3, comma, and then 4 minus 2. Okay, so the -2 minus 3, that's -2 plus 3, so that's going to be 1, comma 2. Okay, so that would be our component form of that vector. All right, and let's do the same thing with this one. I know it's getting messy on the screen, but this will be 3 minus 2, comma, and then the y components, that's going to be -1 minus -3. Okay, so that's going to be 1, comma, and then -1 plus 3, that's going to be 2, like this. And that's our component form. And again, we said they were equivalent, and so it makes sense that they would have the same component forms, because all the component form does is it has only the magnitude and direction encoded in it. Okay, so that's the idea with this. Angle bracket notation is really the way that we're usually going to represent vectors. Like this. Sometimes we'll mention the initial point and the terminal point, but that's more when we talk about applications that kind of comes into play. Okay, so let's talk about some ways that we can do things to vectors, all right? Some operations on them like addition and multiplication and so on. So the first one is what's called scalar multiplication. And in a real way, like all the scalar multiplication does is it makes a vector larger or smaller, okay? So it just changes its magnitude. It does not change its direction. Okay, I guess it sort of changes the direction, and that it can do the opposite direction, but basically it doesn't change the direction. All right, and so we have this, and for a lot of this, I'm going to talk about the geometry of it. And so if I have this vector, and let's say it has magnitude 3, like this, okay, and let's call this v. If I were to do 2v, then what that's going to do is that's going to make the magnitude be twice as big. All right, so it would be here, and then we're going to do another copy. Since we're doing 2v, it'd be 2 copies of v, and so 2v would be this. Okay, and notice that's going to have magnitude 6. Okay, and that's all scalar multiplication does. If you multiply a vector by a negative, okay, so like we have this vector v. If I were to do -v, like this, then it would look like this. Okay, so it'd still be magnitude 3. It would just be pointed in the complete opposite direction. Now, scalar multiplication, it can only change direction by being, the same, or it can just flip it. Okay, it can't like rotate it or anything like that. All right, so let's keep on going. Okay, so next is vector addition. Okay, and so vector addition, the way this works is you just add the components. I guess up here maybe I should actually do a more concrete example. So if I were going to do like 2 times v, where v is the vector 1, 7, -6, then what I would do is 2v is going to be 2 times 1, comma 2 times 7, comma 2 times -6. Okay, so all you do for scalar multiplication is you just multiply each of the components by the number. And so this is 2, 14, negative 12. Okay, so that would be 2 times v. And I mean, that's the scalar multiplication really doesn't get more complicated than that. All right, so next is vector addition, and vector addition, it does kind of a weird thing, but it works out because like if you have forces and you add the forces, then the thing you end up with vector addition is would be the sum of the forces. But this is how it works. Okay, so if I have u right here, and I want to add v to it, like this, then the way I do it is a lot of times they'll call it the triangle method or the parallelogram method or things like this. But what I'm going to do is I'm going to take a new copy of v, okay, and I'm going to put it right there. Okay, that looks pretty close. Okay, and then I'm going to take a new copy of u and I'm going to put it right here, and they'll always match up. Just because that's the way this works. And then u plus v, what it is it's the vector that goes right in between. Okay, so this vector right here, that is u plus v. Okay, so that's how the geometry works. If I am going to do the actual numbers, like if I have 2, 3, plus 4, 7, like this, all I do is I add the x components, so that's 2 plus 4. I add the y components, that's 3 plus 7, and that ends up being 6, 10. Okay, if I had z components, I would add the z components at this point. That's how it works. Okay, and let's keep on going. All right, so next we're going to subtract vectors, and subtracting vectors, I'm not going to do a number example. I just wanted to show you kind of how the geometry works. And so when we add vectors, they do this, right? Like I have the u here, I have the v here, and the u plus v ends up being sort of in between them. When you subtract vectors, it's quite a bit different. If I do u minus v, I have the u and the v here, and the u minus v, it actually goes from the tip of the thing you're subtracting to the tip of the thing that you're subtracting from. Okay, so that's how that works. The reason that this is true is because, like, if you notice, if I say v, and then if I say v plus u minus v, like this, then what I'm going to end up with is u. Okay, and if I actually take this and I have the v here and the u there, like that, then basically using the parallelogram rule, that's why u minus v would be in the middle there. All right, so that's how that works. That's subtracting vectors, and let's keep on going. All right, so next we have magnitude or length of a vector. We talked about this before. We said that's the length of the vector, but this is how you would actually calculate it. Okay, and basically you use the Pythagorean theorem. There's really not much more to it. If you have 3 components, you have an extra little note there that you're gonna use, and the way that this works is we just do the x component squared, the y component squared, the z component squared. We add them up and we put a square root over the top. All right. So we have these two vectors. Let's find first the magnitude of a, and then the magnitude of 3a plus b. Okay, so notice I use 2 different notations here. They mean exactly the same thing, whether you use 1 bar or 2 bars. Sometimes when you have 2 bars, that means something slightly different, but in this class, it does not mean anything different. Okay, they mean exactly the same thing. Okay, so keep in mind the magnitude of a vector, right? Or like this symbol of a vector. That doesn't mean make them all positive, right? That means actually take the length of the vector. All right, so anyways, let's do this. So magnitude of a, we're just going to use the formula just directly. So the magnitude of a is going to be the square root of 1 squared plus 4 squared plus negative 2 squared. All right, let's see if we can do our arithmetic right. So 1, oops, I already said 1 squared. Let's undo that. All right, so that's 1 plus 16 plus 4. And that looks like the square root of 21. Okay, and that's it. Okay, so next let's do the magnitude of 3a plus b. And I'm going to go ahead and just do 3a plus b first. Okay, and then we'll take the magnitude of it. All right, so 3a plus b, like this. Okay, so let's do 3a. I mean, so a is 1, 4, negative 2. And then b is negative 3, negative 8, 9. So 3 times 142, that's going to be, well, let's just do all the steps. So 3 times 1, 3 times 4, 3 times negative 2, and then plus negative 3, negative 8, and 9. Okay, so that's 3. 3 times 4 is 12. 3 times negative 2 is negative 6. And then plus negative 3, negative 8, and 9. All right, and then we have 3 plus negative 3, so that's 0. And then 12 plus negative 8, that's 4. And then negative 6 plus 9, that's 3. And that's, well, I guess that's not quite our answer, but that's our first step, because now that we have this, now we're ready to go ahead and take the magnitude of that. Okay, so the magnitude of 3a plus b, let me put little hooks all over everything. So that's going to be the square root of 0 squared plus 4 squared plus 3 squared. So that's the square root of 16 plus 9, which is the square root of 25, which is 5. All right, let's keep on going. All right, so these are some properties of vectors. We're not going to go through these too much. It's just, vectors have a lot of nice properties. That's why people study vectors, is because, they're commutative and associative. Like they have a lot of things that we're really familiar with that makes them sort of nice to study. All right, you can kind of look over those if you want. Next are unit vectors, and what a unit vector is it's just a vector of magnitude 1. Like that's really all it is. And if you remember up here, when we wanted to scale a vector by 3, like we wanted to make it, or I guess we did it by 2, we wanted to make this vector twice as long, and so we multiplied the front by 2. Okay. On the other hand, if this vector was magnitude 3, and we actually wanted it to be magnitude 1, well, then we would multiply it by 1/3, right? Because 1/3 times 3, that would give it a length of 1. And when we're looking for unit vectors, that's how it's going to work. Okay, so whatever we do, if we want to turn the vector v into a unit vector, what we do is we multiply it by the reciprocal of its magnitude. Oops. Okay, so here we go. All right, so for example, the vector was magnitude 2, we would multiply it by 1 over 2. If it was magnitude negative 100, we'd multiply it by 1 over negative 100. Okay, and that's how it works. All right, and so you can kind of see here. Here's a picture of a unit vector. Here's a picture that's supposed to not be a unit vector. And so what we want to do here is we want to find a unit vector in the direction of the vector 3, 2, negative 1. Okay, and this one's kind of messy, I think, if I recall correctly, but that's fine. I mean, some of the ones in the homework are going to be messy too. And so whenever I'm trying to turn a vector into a unit vector, what I want to do first is I want to find the magnitude of the vector. Okay, because remember, to turn it into a unit vector, we multiply by the reciprocal of the magnitude. Okay, so let's do this. Okay, so the magnitude of 3, 2, negative 1 is going to be the square root of 3 squared plus 2 squared plus negative 1 squared, which is the square root of 9 plus 4 plus 1, which is going to be the square root of 14. Okay, so far so good. And so now our new vector u is going to be 1 over the square root of 14 times 3, 2, negative 1. Okay, because this vector 3, 2, negative 1, it has magnitude square root of 14. So to turn into a unit vector, I need to divide by square root of 14, right? And so our final answer will just be 3 over square root of 14, 2 over square root of 14, and then negative 1 over square root of 14. And that's it. All right, and you might be wondering, like, do we have to rationalize denominators? No, you don't have to rationalize denominators. And mostly in this class, you're not really going to have to simplify anything. But in particular, you certainly don't have to rationalize denominators or anything. Okay, so let's do one more. This one's a bit different, but it's the same idea. Instead of turning it into magnitude 1, now we want to turn it into magnitude 5. And so what we're going to do is we're going to turn it into magnitude 1 and then multiply it by 5. Okay, so I mean that's kind of the idea. All right, so again, we're going to find the magnitude. Okay, so I mean, who knows? Maybe it's already 5, and then we don't have to do any work. Okay, so it's going to be square root of 9 squared plus 2 squared. So that's square root of 81 plus 4. So that's going to be the square root of 85. Okay, so now our unit vector will be 9 over square root of 85, comma 2 over square root of 85. Okay, so this thing has magnitude 1. All right. And now that it's magnitude 1, I want to multiply the whole thing by 5. Okay, so 5u, let's see, 5 times 9, that's going to be 45. So 45 over square root of 85, and then 10 over square root of 85. And that's our answer, okay, because that has magnitude 1. Or I'm sorry, magnitude 5. See, and I mean, like, also, if now I was to ask you, like, all right, well, now I want one with magnitude 346, then all you would do is you go back to your magnitude 1. You'd go back to your unit vector, and then you would just multiply by 346. Okay, so I mean, I mean, it's kind of nice, right? I mean, you just have to turn it into a unit vector, and then you can have any size vector that you want. Okay, so the last thing we're going to talk about are standard unit vectors, and you've probably seen these like I, J, and K. Sometimes they call them standard basis vectors. There's several different names for them, but what they are is they just amount to a different way of writing vectors. Okay, so I, J, K, that is a unit vector. I mean, you could check like square root of 1 squared plus 0 squared plus 0 squared. That definitely equals 1. Same thing for J and K. In the plane, they would look like this. They're just like in 3 space, but they have just 2 components. And the idea is that, since they're so simple, it's really easy to write a vector as what's called a linear combination of I, J, and K. Okay, so let's express this vector as I, J, and K. And the way to do it is like this. So whatever the X component is, I multiply that by I. Whatever the Y component is, I multiply by J and then by K. So this will be 4I plus 0j minus 3k. Okay, and then you can even simplify that to be 4i minus 3k. Okay, and that's your answer. All right, and if you're skeptical that this is actually the same thing as 4, 0, negative 3, I mean, you can just say 4 times, and then I, that's 1, 0, 0, and then minus, and then 3 times, and k is 0, 0, 1. Okay, so that's 4, 0, 0 using scalar multiplication. And then this will be plus 0, 0, negative 3, like that. And then if you do, vector addition here, we got 4, 0, negative 3. And then of course it's the same thing. Okay, so that's it. In the next section, we're going to talk more about the 3-dimensional coordinate system, and we'll talk more about 3-dimensional vectors and things like that. And I will see you then.